Current estimates place the total number of stars at around 200 billion trillion throughout all of space. With all those blazing suns radiating light in every direction, logic says the night sky should be as bright as daylight. Yet when you look up at night, you see mostly darkness. This contradiction stumped astronomers for over 400 years until recent discoveries from the James Webb Space Telescope finally revealed the shocking truth about why our universe remains dark. The fundamental mystery that stumped scientists. This contradiction forms the foundation of what astronomers call Olbers Paradox, named after Heinrich Olbers, who formalized the problem in 1823. The mathematical logic appears unbreakable. If the universe extends infinitely in all directions and contains a uniform distribution of stars, then every line of sight from Earth should eventually intersect with the stellar surface. This means the entire night sky should glow with the combined brightness of all those stellar surfaces, creating a luminosity comparable to staring directly at the sun's photosphere. Johannes Kepler first recognized this astronomical puzzle in the early 1600s when he observed that the darkness of night seemed to contradict the infinite universe model that many scholars accepted. Kepler reasoned that if space truly contained endless stars stretching to infinity, the accumulated light from all those distant suns should make nighttime as brilliant as day. The fact that darkness dominated the night sky led Kepler to conclude that the universe must have boundaries with a finite number of stars distributed across a limited volume of space. Yet Kepler's finite universe solution created its own problems. If stars existed only within a bounded region of space, what lay beyond those boundaries? The concept of an edge to the universe raised uncomfortable questions about what might exist in the void beyond the stellar realm. These philosophical implications troubled scientists who preferred elegant, unbounded cosmic models that avoided arbitrary limits on the universe's extent. The paradox gained renewed attention during the 19th century as telescopes revealed ever more distant stars and nebulae. Each improvement in observational technology uncovered additional layers of cosmic structure, suggesting that the universe contained far more luminous objects than previously imagined. Heinrich Olbers approached the problem with mathematical rigor, demonstrating that even accounting for the inverse square, law of light intensity, an infinite universe with uniformly distributed stars would still produce a blindingly bright night sky. Olbers calculated that while individual distant stars contribute less light due to their remoteness, the sheer number of stars at each distant shell would compensate for this dimming effect. In an infinite universe, the number of stars within successive spherical shells increases as the square of the radius, exactly canceling out the inverse square reduction in brightness from each individual star. This mathematical relationship meant that stars at every distance would contribute equally to the total sky brightness, making the darkness of night theoretically impossible. Several 19th century scientists proposed solutions involving interstellar dust that might absorb starlight before it reached Earth. They suggested that cosmic dust clouds scattered throughout space could block the light from distant stars, explaining why the night sky remained dark despite containing countless luminous objects. However, this dust absorption hypothesis contained a fatal flaw. Any material capable of absorbing enough starlight to darken the night sky would eventually heat up and begin glowing itself, ultimately contributing its own thermal radiation to the cosmic brightness. The paradox challenged fundamental assumptions about the nature of space, time, and cosmic structure. If the universe truly extended infinitely and had existed for an infinite duration, then light from every possible stellar source should have had sufficient time to reach Earth. The mathematics suggested that under these conditions, the night sky should shine with an intensity of approximately 200,000 times brighter than the full moon, creating perpetual daylight conditions across Earth's surface. Early 20th century astronomers began recognizing that the darkness paradox might reveal something profound about cosmic evolution and structure. The problem forced scientists to question whether their basic assumptions about the universe's properties might be fundamentally incorrect. Perhaps the universe was not infinite in extent, or maybe it had not existed for an infinite duration, or possibly the distribution of stars was not as uniform as previously assumed. The stakes of solving this paradox extended far beyond academic curiosity. The darkness of night touched on fundamental questions about the origin, evolution, and ultimate fate of the universe itself. If scientists could understand why space appeared dark, despite containing enormous numbers of luminous objects, they might unlock secrets about the cosmic timeline, the universe's geometry, and the physical laws governing light propagation across vast distances. The paradox also connects to everyday human experience in profound ways. Every person who has ever looked up at a star-filled night has witnessed this cosmic mystery firsthand. The sense of awe and wonder that darkness evokes stems partly from the subconscious recognition that something about the night sky defies our intuitive expectations. Our brains evolved to associate brightness with safety and darkness with potential danger, making the cosmic darkness feel both beautiful and slightly unsettling. Current research suggests that solving Olbers' paradox requires understanding multiple interconnected phenomena that were unknown to 19th century astronomers. The expansion of space itself affects how light propagates across cosmic distances, while the finite age of the universe limits how much light has had time to reach any given observation point. Additionally, the universe's structure is far from uniform, with matter concentrated into galaxies and galaxy clusters separated by vast empty regions. The paradox ultimately revealed that the universe possesses a hidden architecture that completely contradicts our intuitive assumptions about cosmic brightness.